Hello and welcome back to another episode of the Natural Number Game in Lean 4. Today we'll be tackling the proposition world. What is a proposition? Well, it's a true or a false statement like 2 plus 2 equals 4 or 2 plus 2 equals 5. And just like we can have concrete sets in Lean like the natural numbers or abstract sets like x, p, q, we can also have concrete propositions 2 plus 2 equals 5 and abstract propositions called things like y. Okay, nice. And then so we have p as a prop. Something like this. And then we'll see some propositions in action. And then in this world, we're going to learn about manipulating propositions and proof. And the tactics we learned last time in the function world, namely intro, exact, have, and apply, will also be useful for this world. Okay, so we have this example, which looks similar to our first example, except, well, this is on line 5. We have prop instead of type here. And then we can prove this, I think, the same way. Exact HP. Cool. Let's move on to the next example. Intro. Let's prove an implication. Your goal is to prove P implies Q. We have a lemma. Nice. Lemma. So I think for this we want to import a lemma. Okay, implies self. P implies P. Well, we can intro P, so P implies P. We can start with just a P, and if we have a P, well, then exactly P is what we have. So given P, we can get P. Nice. Have, level 3 have. Okay, well, I kind of see what's going on here. This seems to be just like the exact same thing as that. I think there's a correspondence. Curry-Howard correspondence or something like that. Let me check what it's called. Curry-Howard. Oh yeah, the Curry-Howard isomorphism between programming language theory and proof theory that, well, there's a relationship between computer programs and mathematical proofs. And so I think there's a equivalence between defining functions on types and proving things with propositions. And I think that's what we're seeing now. Okay, how do we solve this one? Let's see, we can have, I'll just do the exact. So we want to get U, so we'll have L on something that's T, on J on something that's Q, H on something that's P, P. And can I delete parentheses here or no? No, I can't. Okay, that solves that. Lemma maze. Okay. Oh, so apparently I should solve this one with have. I'll just leave it as exact. 1, lemma maze2, apply L, oops, I forgot by, apply L, apply J, apply H, exact P. Cool, apply makes it easy. Example, P, Q propositions. P implies Q implies P. Intro, P, Q, exact P. Nice, and I guess we could just have this be the same way as the previous time, where we have the underscore for the unused thing that we introduce. Okay, what does intro do? It introduces one or more hypotheses, optionally naming and or pattern matching them. Cool. Intro can be combined with pattern matching, much like fun. Okay. Let's move on. Well, intro ABC. And then exact, what do we want to apply? We want to A of P. Wait. So B of C gets us as type Q, and then B of C, A of B of C. Okay, what does it say? Application type mismatch A, B, C, effect type P, A of P. Is that what we want? Oh. No. Oops, what is this P? We don't know what P is. A of C. P of C, is that what we want? Yes. Because A is something that takes two things. The first thing is something that's P. Something is something that is Q. And it gets us R. Cool. Blazing through the proposition world. Function world. Oh, lemma. Okay, well, I think the cool thing is we're getting names for all these things. And this gives us, okay, if we intro HPQ, HQR, we have P to Q, and then we have Q to R, and then we can get P to R. This level is really about showing the transitivity of implies. Okay. Is it just exact HPQ, HRQ? Does that work? Let's type Q to R. Oops. Can we swap it? No. Well, let's do one more. P. Exact. What do we have? We want to apply HQR on HPQ of P. Cool, that's implies transitive. So P implies Q and Q implies R, implies P implies R. Nice, nice. That is an important lemma or theorem for sure. Oh, this level's cool. we're doing contrapositive this time. Lemma contrapositive. P implies Q, implies not Q, implies not P. Intro A, B, C. That's cool. So we have A, B, C. I guess this contrapositive thing is similar to, yeah, Q implies false, implies P implies false. Or an F implies empty, but this does feel a little different. Q, I guess that's like the correspondence of what is not Q. Logically not Q in the function world is Q gets sent to empty. But how the heck do we prove this? The false, okay, if there's a false proposition false with no proof, it is easy to check that not Q is equivalent to Q implies false. And in the natural number game, we call this not if and only if implies false. You can start with the proof. Okay, let's figure out this if and only if implies false business. Okay, so I was trying to figure out how to define this as a new lemma and use it, but I was unable to figure it out, so we're not going to use this lemma. In Lean 3, this is defined as an axiom using some reflexive thing from if and only if. I don't know if it's that simple, so I will just intro ABC. And then we can just apply things in a certain order. So we can apply, let's see, C, B. Okay, yeah, if we apply B and we negate that, we're left with Q. Apply A and exact C. So this proof is just the same as we did for the function world, BAC, BAC. Cool, let's move on to a big maze. So we have this CC tactic. In Lean 3, I don't know if we have something in Lean 4, but we can figure out some stuff here. Well, previously we did a bunch of exacts. Yeah, we could probably do the same thing. So I'm just going to copy this over and see that it also works with propositions. Cool. This is the proposition world. We used a lot of the same things, pretty much all the same things as the function world. And it was a lot of fun. Nice. Next time we'll be working on to let's see what world is next. We have the advanced proposition world where we'll actually do cool new tactics like split cases, left, right, and X falso. Thanks again for watching, and yeah, please leave a like and or a comment. Have a great rest of your day. Hello again, this is a quick bonus part to the position world video, I figured out how to solve this not if and only if implies false. So first thing, if I rewrite using not, where I first need a open lean and open core, maybe just open lean. Now I need both. I need to get the core as well, because core is what contains all these definitions. Like false and stuff. I need to have false with a capital F. Afterwards I can apply, or I can exact if dot refl, or refl, where this is defined in core.lean as a is if and only if a, where a is a proposition, and which is exactly what we have in our case after we rewrite with the not. And I think we could have actually done it without rewriting with the not, as long as we use this capital F false. But if we use lowercase f false, this is bool.false, and this is the false proposition. So that was my mistake earlier, using the lowercase false instead of the uppercase false. As you can see in our function world, or yeah, we didn't have anything in the function world. Okay, so now after we do this, we can solve contrapositive differently. We can first rewrite not if twice, state something like this, and then here matches what we start with here. And so with that, now we can just do an intro A, B, C. Apply B, apply A, exact C. Apply B, apply A, exact C. Thanks for watching. Just wanted to add this a little bit now that I figured this out. The issue was using the lowercase false from lean 3, but in lean 4, uppercase false is the prop false, and lowercase false is the bool false.